If this is recorded, where will you post it?
Hopefully Canvas. That's my hope.
Canvas?
Yep.
In the media tab and stuff?
That or the files. Yeah, one of the two.
Alright.
All right. Okay. So first up, this formula. This is talking about Henry Darcy in his formula, but what this actually is just the Bernoulli's equation, and I can show it to you by adding this term. Take it easy. So when I put it like this, my pressure term here is similar to my internal energy term. My term that I added on here is my gravitational energy. And this new term that looks different, that's our a kinetic energy term. So as you can see, this is why it looks familiar to us. Now, if I were to draw a picture of this, I get the following picture. So it's a pipe flow between 2 points, and it's completely horizontal in order to neglect that gravitational energy term. Okay, now in this problem, we want to plug in the dimensions into this problem and determine the dimension of this alpha term that we have. So when we do these kind of problems in fluids, we refer to mass as uppercase M. We refer to distance as uppercase L. And we refer to time as uppercase T. And temperature as theta. Okay, so in this, yes?
Do you mind just going back into the first question?
Yes.
It's perfect, thanks so much. That's all I need.
Yeah, no worries. So, yeah, in this equation, we have 4 variables that we're looking at and 1 unknown. So, we have delta P, which is pressure. In terms of SI units, it would be newtons per meter squared, which is a force over area. In terms of dimensions, that would be mass times acceleration, so L over T squared. And area is just unit length squared. Next up is density, rho. For rho, we have kilograms per cubic meter, which is mass per volume. And in terms of dimension, it's M over L to the power of 3. We have length, it's just L. And for velocity, that's meters per second, and that would be L over T. Once again, just for a reminder, our equation is delta P over rho equal to L alpha L V squared. So let's plug in the dimensions. So we have our pressure term, our density term equal to alpha times length over time squared. All right, so let's work on the left-hand side first, because it's the most complicated. I see my mass units cancel out. For the numerator, I see this L cancel out with this L squared. And I'm now going to group these units together to get the following. Okay. So right-hand side is alpha L cubed over T squared. On the right-hand side, I get 1 over L T squared over 1 over L cubed. To isolate alpha, I'll multiply both sides by T squared over L cubed. So the following units will cancel out. And as a result, I'm left with the following. Alpha is equal to the units of 1 over L, which is similar to L to the minus 1. And this kind of makes sense because alpha is associated with the Darcy friction factor. And this term is a coefficient of our kinetic energy term. And that's the units of alpha. Any questions about this problem? If not, next problem is pretty similar, so let's just hop to that. So here, I run it already, but now we're looking similarly, another pipe flow problem, but instead, here we're looking at the velocity profile rather than like the energies. So here we see Poisson's flow, I believe, and this is a parabolic velocity profile given by this equation here. So this equation is good for it captures the no-slip conditions at the boundaries of our pipe, and our maximum flow will be at the center line of the pipe. Okay, let's once again take the variables in this equation, turn them to the non-dimensionalized forms, and then plug it in to solve for B. And I'll rewrite the equation in a bit. So I believe first is velocity U. U is length per unit time. Delta pressure, we did that earlier. It was mass length times squared over length squared. If I were to simplify this, I would get mass per length times squared. So now it's viscosity is a new one. When I look at the textbook tables to like get my viscosity values, I usually see viscosity represented as kilograms per meters per second. So if I were to non-dimensionalize it, I get the following. It'd be mass over length units times unit times. So it's similar to the pressure term, except the T isn't squared. Finally, last one is our radial location, and that's shown by r squared minus r naught squared. R is a length or a distance. So if it was non-dimensionalized, it'll just be L squared. So those are our 4 terms. And here's the equation just once again. Sorry, I got the knots mixed up. Okay, let's plug it in. So for U, I get L over T equals to B times mass per length T squared for pressure, and mass per length T for viscosity, multiplied by the radial location, so L squared. Let's simplify that right-hand side. This fraction simplifies down to just 1 over T. And we're left with the L squared from our radial location. Multiplying both sides by T over L squared to isolate the B term. We get the following. B is also equal to 1 over L. And that's the parameter for that pipe flow. Poisson's parabolic velocity profile. Okay, I mean, very similar to the other problem. Now let's jump to a more complicated problem. So here we are. I'll quickly read out the problem description. We have a thin plate in the middle, and this thin plate is sandwiched between 2 fixed plates. And both sides of this thin plate has a different liquid associated with it. Additionally, this plate is kind of at a is not between directly between these 2 fixed plates. It's at a random location with a certain height associated between that and the top surface, and a certain height between the bottom surface and the bottom plate. We have a contact area for the center plate that is in contact with the fluids, and for the first part of this problem, we're going to assume a linear velocity distribution within the fluids, and we want to find out what force is required on the center plate in order to maintain the velocity v. So I guess first things first, I'll write down my assumptions. So here's my first assumption. My first assumption is that I can neglect any velocity in the y direction. I'm referring to this as in like the direction of the height between the plates. And that's because I only want to focus on the horizontal direction in which the force and velocity is being applied or occurring at. So which also kind of begs the question, I also need to define my origin. Also my coordinate system. And the last thing that I'm going to assume, based on the problem statement, is we have a linear velocity profile. Okay. That being said, I'm not going to come back to this image real quick. I want to first draw out my contact area. Contact area A. Okay. So let's talk about applying the force to this the thin plate. The reason we're doing so is when we're pulling this plate at a certain velocity through the fluid, there's some kind of resistance due to the fluid, kind of like, dragging the plate back. That's the viscous force that we discussed in class. So we have a viscous force going against the direction of the plate, opposing the motion. Viscous force. And this viscous force is due to our shear stress at the plate. I'm not sure. I think it's called the middle plate times the contact area. So once again, we're going to assume a linear velocity profile, which means that. So we have here. I draw a line here to represent, I guess, 0 for now. Which means that at the top surface here, we have it's in contact with the fixed plate, meaning that this location, due to the no-slip condition, the velocity there is 0, and the fluid in contact with the middle plate that's moving is going to inherit the velocity of that plate. So fluids along the plate will have the velocity v. And the linear velocity profile means that as we go through the fluid, we should see the velocity changing linearly. And once again, I will define my coordinate system here. X along the plate, Y perpendicular to the plate. Okay. With everything set up now, let's talk about boundary conditions. As I said, the fluid is inheriting the velocities of the plate or the surfaces that it's in contact with. So at this middle plate, at y equals 0, our origin, we see that the velocity at 0 is equal to the velocity of the plate, v. It inherits that speed. At this top surface, at y equals h1, we see the velocity at h1 is 0. It's a fixed plate. And this is the top surface. I'm going to label it 1 for fluid 1, or regime 1. So, boundary conditions at the surface of that plate, we have velocity of the plate. At the velocity at the top plate, it's fixed, so no velocity. It's a linear velocity profile, so we know that u is equal to m for slope times y plus b. And we have 2 points, so we can solve for this linear profile. We're going to get the slope first. So rise over run is how people usually memorize it as. I think of it as the dependent variable over the independent variable. So okay, so here that's the formula. I'm gonna plug in my variables. So I get my slope. My slope is negative v over h1. Okay, now I'm gonna solve for b using one of these parameters. I'm gonna pick this parameter using point slope form. So u of y minus 0 equal to the slope multiplied by y minus h1. That's point slope form. Solving for u1 of y, I get the following. So this is the velocity profile for that top surface. Oh, sorry, for the above the plate. Okay. In class, we talked about Newtonian fluids, and for Newtonian fluids, we know that the shear stress of that of our plate, the top surface of our plate, is equal to mu viscosity of the fluid we're in, multiplied by the velocity profile derived with respect to y at that plate. So we derive the equation up here. Doing so, h1's a constant, y is a variable, so that derivative gets us mu times negative v over h1. That's the shear stress for the top surface. Let's talk about the bottom surface. We need to reorientate our coordinate system because for the bottom surface of the plate, we're looking down. So now we're going to find downwards as our positive y direction and keep x along the direction of the force and velocity vectors. Once again, as I'm along the plate, I inherit the velocity of the plate. At the bottom plate, the fixed bottom plate, there's no velocity. Therefore, I get another linear velocity profile. Okay, once again, at y equals 0, u0 is v. At y equals h2, h2 equals 0. Once again, that's my boundary conditions. And this is regime 2. Solving it's very similar to the top part, so let me go through it quickly. Boundary conditions, u0 is v. And once again, this is in respect, or with respect to our new coordinate system. h2 is 0. Linear profile, solve for slope. Sorry, I got it backwards. My slope is negative v over h2. I'm going to use point slope form now, using this one. u2 minus 0 equal to slope, negative v over h2 times y minus h2. Therefore, my velocity profile beneath the surface of the plate with respect to our new coordinate system is the following. V over h2 multiplied by h2 minus y. So, the shear stress at the surface of the bottom surface of our plate is equal to viscosity, mu2, viscosity of the bottom, viscosity of the fluid at the bottom, times velocity profile derived with respect to y at plate. Okay, everything's getting mixed up. And that would get me mu2 multiplied by negative v over h2. So now we have the shear stress, and this shear stress value is constant throughout the fluid region because it's linear, therefore it's the same. If we had that like parabolic flow, the shear stress would be changing throughout the fluid, but here, not so much. So as I mentioned before, F, the viscous force is equal to the shear stress multiplied by contact area. And I'm going to sum up my two forces. So I have the upper surface was mu1 over h1 times velocity times contact area, and I had my bottom surface, mu2 over h2, both negative by the way, times velocity times contact area. Therefore, the viscous force is equal to velocity negative velocity times area multiplied by mu1 over h1 plus mu2 over h2. That's what we get. I guess to maintain equilibrium, the force being applied to the plate should counteract the viscous force. Therefore, we have our force value being the positive value of the viscous force. Any question? Okay. Give a little more time for the next problem, and after this problem, I'll let you guys go. Okay, I just finished writing it down. I want to read this real quick. I was reading about it yesterday. I think it's Piaget's theory, but essentially, children, when they get to 2 years old, they develop a thing called a concrete development stage or concrete operational stage, and that's when they can understand the idea of conservation of mass or matter, and that's going to be really important for this next problem. Okay, so this next problem is about gas dynamics. So the problem statement, for a flow of gas between two parallel plates, this figure refers to Couette flow, which is, all it means is a linear velocity profile. But they want to reanalyze that case and consider the fact that there's slip flow occurring at both walls. Slip flow, I guess I'll talk for a little bit, or talk about that in a bit. And we're gonna apply the slip condition here. Delta U wall is equal to L times du over dy, and L is the mean free path of the fluid. Essentially, in gas dynamics, if the molecules are heated up enough or excited enough, they can move around on its own. So even in contact with the surface, which it should inherit the velocity of that surface itself, gases could have slightly different velocities due to the fact that they're moving around on their own. And L refers to the mean free path of the fluid, which is how the length or distance that a gas molecule can travel before it collides into another gas molecule. And usually that's in terms of like nanometers or like picometers, so it's usually pretty negligible. But that's the problem we're working with. Okay, let me draw that Couette flow again. So a fixed surface, and we have a moving surface on the top, giving us the following velocity profile. So we should be used to this by now. So that's what it normally is. When I apply the slip condition, this happens. I think I draw it better, but it's something along these lines. So usually our boundary conditions for no slip would be with this given coordinate system. Velocity at 0 is fixed, so is 0. Velocity at the top surface should be v, the velocity of the moving plate. However, dealing with slip, we get the following. Our initial velocity at the bottom surface isn't 0. It's delta U wall, which is the slip velocity. At the top surface, what we would get is velocity of the top plate minus slip velocity at the wall. So these new boundary conditions will give us a more skewed slope, as you see here. And the reason for this being this way is if we were to integrate the velocity profile from the bottom plate to the top plate, it should be equal to that integration for the no slip condition. The integral should be the same for the slip condition because mass is conserved and the velocity profile should be the same. That's why we have this new profile, as I showed here, that is different. It's to account for that fact. Okay, so that's a new boundary. That's why we have our new boundary conditions, as well as a new slope, because of conservation of matter or mass conservation of volumetric flow, one of those two. All right, moving on. We're gonna now solve these two problems. We want to find the expected velocity profile as well as the shear stress associated at each wall. So we have two boundary conditions, and we assume, and we also assume a linear velocity profile. Similar to before. Now we apply new boundary conditions. So let's start with this first one. So u0 is equal to the slope times 0 plus b equal to slip flow. And that makes sense because at the origin, which is here, the slip flow at the fixed wall should be the slip flow. Or the velocity to the wall is the slip flow. Okay, and we'll hold that on for now. Using our second boundary condition, we get the following. UH is equal to the slope times h plus b. And we know b is the slip flow, equal to velocity of the moving plate at the top minus the slip flow. Okay. I'm going to basically look at this delta U term. So we're given for that the delta U, or the slip flow, is equal to the mean free path of the fluid multiplied by du over dy, wall, I guess, to be more specific. Du over dy, that's just our slope here. So, therefore, we can rewrite our slope as, I'm gonna rewrite my slope as in terms of this form, and also break down my delta U formula into the equation that represents it. So I have du over dy times h plus L times du over dy equal to v minus L du over dy. So I'm now gonna isolate for my du over dy. So du over dy times h plus 2L du over dy. I moved from the right side to the left side, equals v. Isolating for du over dy, I get v over h plus 2L. So that's my slope. And once again, it's just m. So my velocity profile is v over h plus 2L times y plus my slip flow, which I'll just keep it as slip flow for simplicity. So slip flow at the wall, and then by plugging h, I should get this boundary condition back. Okay, now let's get the shear stress at the wall. So that's mu times derivative of the velocity profile with respect to y at the wall. Doing so gives me mu times v over h plus 2L. If I were working, and I'm gonna specify that is v with slip. Oh, sorry, that's shear stress with slip. Shear stress with no slip, as we've seen before, would just be mu times v over h. So, due to the fact that we're working with gas dynamics, and the molecules are excited, we get that 2L term there, which slightly decreases the shear stress at the surface. Once again, L is like in terms of nanometers or like picometers. So the only time that it'll be relevant is if the height or the distance between your two surfaces is within that realm of magnitude. It'll be important. Otherwise, like working with like large pipes and stuff, this is really negligible. And that's the end of my discussion. Thanks for coming.